Okay, how about this first one up here? Why does the boiling point get elevated?
Polarity like changes the structures, right? And then increase the strength that you forces.
I don't know if I wouldn't say polarity.
It attaches itself to water molecules, so when they need to evaporate to the atmosphere, they need to release salt. They need to break the bond.
It's like,
Okay, so
there's like more attractive forces in the water, and so it doesn't want to not be with water anymore.
I wouldn't say that. What's holding water molecules to water molecules? Which is basically saying keeping it from boiling. Which one?
Hydrogen bonding.
So okay, so water is exclusively H bonding, which is a pretty strong partial positive and partial negative. When I throw the salt in there and it ionizes, what intermolecular force do I have now?
Full positive.
Yeah, so I've got partial positives with pluses. Sorry, not pluses, minuses. And I've got partial negatives with full-fledged plus charges. So what's harder to break? These guys are harder to break because the plus and minus are significantly more powerful as far as their ability to attract things than the partials. Freezing point depression? Same reason, right? Same reason, except, but it's not that they're, in the previous one, they're trying to get away. And in the ice, they're not trying to get away, but they're trying to do what? So what I have is the same reason with this, but I've got the crystal lattice structure gets disrupted. And the reasoning behind the crystal lattice getting disrupted is because now I've got hydrogen bonding and ions instead of just hydrogen bonding and hydrogen bonding. So the water molecules reorient themselves to face those pluses and minuses on the cations and anions. Okay, what is the Fahrenheit freezing temperature of this magnesium chloride solution? Okay, so change in the temperature of freezing is equal to N Kf molarity. What's the N for this one? Ions. So what is the number? It's MgCl2 is the formula, and so when that goes into water, it breaks up into 3 pieces. So the N for this is 3.
You wouldn't count the H2 of that.
No, because this is about the solute's effect on the water. And so then I've got 1.86 Kelvin, degree C, molarity, and we said the concentration was 2.5 molar. So in the last problem, we said that the disruption happened because there are ions reoriented the hydrogen bonding in the water molecule. So what about what is this equation doing for us? If the reasoning behind it is water being reoriented, disrupting its crystal lattice structure because the cations and anions are more powerful than the partial positives and negatives that the water molecule has in hydrogen bonding, what is this equation doing for us?
How much that changes.
Yeah, so what affects the change? Well, there's only one thing. There's only one issue now that we know that it's cations and anions that are disrupting it. It's the number of cations and anions that are disrupting it, right? So this is telling me the concentration, right? So that's telling me how many of what? What's this the concentration of? All right. So that's the concentration of magnesium chloride. And that'd be fine and great, except magnesium chloride is not what goes into the water. When it goes into the water, it doesn't stay as magnesium chloride. What does it do? It separates into 3 pieces. So not only do I need the concentration, I need to know how many pieces that thing breaks up into. So it's more like 7.5 molar. Are we okay with that? Why am I saying 7.5 molar? Because that thing breaks up into 3 pieces. So it's 3 times more effective than if I threw in, say, glucose. So glucose, sugar water, actually is a lower freezing point than salt water, but this salt water would be much lower even at the same concentration because that thing breaks up into 3 pieces, becoming 3 times more effective. So we need to make sure we think about the concentration, meaning how many of these actual salt molecules go in, because the more of them go in, the more disruption occurs. Plus, if it breaks up into pieces, then I have to consider how many pieces it breaks up to when it goes into. So if it breaks up into like 6 pieces, then it's going to be much more effective than something that breaks up into 2 pieces or 3 pieces. Okay, so let's finish this. I've got, I don't want that. 3 times 1.68 times 2.5.
Why doesn't it matter whether or not they're cations or anions? Do they not have a different?
It's because the hydrogen bond has a positive side and a negative side.
There's no bond to anything.
So it'll just flip around. The oxygen will be attracted to all the cations, and the hydrogens be attracted to all the anions. So this is 13.79 degrees Celsius. And now this is where it's not hard. It's just you got to think about what's happening here. So I'm asking about the freezing point for Fahrenheit. So do we know what the freezing point now is for Celsius?
No, we know the change.
Okay. Can you do the math in your head?
Negative 30.
Negative 13.95, right? Because water's freezing point is 0 in Celsius. So this is like the little tricky part. You got to remember that this is the change. And change in temperature is equal to the temperature final minus the temperature initial. Well, the temperature final is what we're looking for, right? We're looking for this, and we have the change. And we know the temperature initial is 0. So I do a little bit of subtraction, and I end up with negative 13.95 degrees C is my new freezing point. But I didn't ask that. I asked what it was for Fahrenheit. So then I have to use the Fahrenheit equation. So what do?
Just
Times
times 9 fifths plus 32.
9 fifths plus 32. I think that's right. It's either 9 fifths first or the 32 first. So let's figure it out. So 13.95 times 9 divided by 5 plus 32. Yep, that's right. Because the answer to that I get is 6.89. So with sig figs, I'll say that the answer here is 6.9 degrees Fahrenheit. Does that number make sense?
Yes.
We okay with that? I mean, we're at basically negative 14 degrees Celsius, so I got a number considerably less than 32 because those degrees Celsius are basically about 2 Fahrenheit, right? It's 1.8, but so we're pretty close with that. So that number makes sense. Collide? What do we have for a definition for a collide?
Solid suspended in liquid without distributed. Insoluble material.
How about an insoluble material? It doesn't necessarily need to be a solid.
Is there a difference between a collide and a colloid? Or did I just misspell that?
Yeah. Okay. It doesn't need to be a solid because like an easiest example would be like whipped cream. The solute is actually a gas, and the solvent in that case is actually a solid-ish. Solid, yeah. Like a memory foam mattress, definitely a solid, and it's inundated with a bunch of gas particles or gas pockets in the middle of it. So I'll put whipped cream. And then say, how about fog as another one?
For clouds.
Sure, clouds, absolutely.
Glass.
Colored glass, yeah, absolutely, colored glass.
What?
What? Blood? Yeah. Sure, blood. I'm good with blood. My cell functions. So what do we got there?
Water and earth that likes water and sort of forms with the earth stuff like water.
So we have a sphere. So not just a circle, but the entire surface of the sphere is covered with the part that loves water. And then the rest of the molecule that hates water is on the inside, so it doesn't have to touch the water. So do we remember what those terms were for hates and loves water? And where are these things used most commonly? Soap, yeah. All right, lists the following order of most and least effective at reducing the freezing point of water. All right, so what's the most effective? So when we were talking about this equation up here, we were talking about this stuff, right? Yep. 3 pieces, 2 pieces, 2 pieces, 0 pieces. Well, let me rephrase that. How about one piece? We okay with that? So the first one is obvious because it's a sodium, so it splits. Don't get yanked into thinking that nitrogen and those oxygens separate, because that's a nitrate and it stays together as a particle, so that's still just 2 particles. The calcium chloride is like the magnesium chloride, since calcium and magnesium are in the same column of the periodic table, so it'll break up into 3. And barium sulfate's insoluble, so it doesn't break up at all. So it's actually just kind of like throwing dirt into the water or sand into the water. It'll reduce it just because there's stuff there, and agitation can get it to disrupt the crystal lattice structure. But barium sulfate would be incredibly bad at dissolving or melting it. It would be okay to put traction on it, though. Like if you had ice all over the place and you threw barium sulfate down, you could walk on it a lot easier because the stuff literally would not melt. And so there'd be something on top of the ice that you could adhere to. But it would not melt the ice at all. So the calcium chloride, since it breaks up into 3 pieces, it's got the most particles to calcium chloride's got the most particles to disrupt that water crystal lattice structure. So if you put the same number of calcium chlorides and the same number of sodium bromides into the water, onto the ice, what would you expect to happen? You get 50% more melting out of the calcium chloride. It'd be 50% more effective. Do we remember what another reason why this stuff here would be better than this stuff right here? Corrosion, and this kills plants. So we wouldn't want to throw that around. I mean, unless you're at the beach, I suppose. Those plants are used to it.